Many of us have been mesmerized by the skipping of water striders over the surface of a pond. How is it possible that these insects can use the surface of water like an elastic membrane? Moreover, the effect is not unique to water striders. We can carefully place a paperclip, a needle or even a coin onto the surface of water and it will float, creating an indent on the surface. Just as the water strider, these objects are heavier than water and should submerge. You might have guessed it already. Here we have another interesting phenomena arising from the high surface tension of water. The feet of the water strider are hydrophobic, meaning that they are water repellent like a wax surface or a lotus leaf. A drop of water on a hydrophobic surface forms a dome as shown in this photograph and my drawing underneath. The water tries to minimize its contact surface to the hydrophobic solid underneath. We can draw the surface tensions between the three phases: gas, liquid and solid. In this configuration the contact angle θ is larger than 90 degrees. Here we see a cross-sectional drawing of a water strider foot. The weight of the water strider causes the surface of the water to bend downwards. Since the foot is hydrophobic, most of its surface resides in the air. In order for us to see more easily the analogous situation of the foot of the water strider and the water droplet sitting on the hydrophobic surface, we have to rotate the perspective. At the edge of the foot, where all three faces meet, we can set up the same surface tension balance, finding the same large contact angle as before. Back in the normal view, I have also drawn the vector for the gravitational force resulting from the weight of the water strider pointing down. Now we remove the two solid fluid surface tensions from our drawing since they act within the solid surface and do not contribute to the force balance here. Additionally, I have drawn the vertical component of the water-air surface tension and the three-phase contact parameter P around the foot of the water strider. The water-air surface tension pulls the foot along this parameter into the air since the high contact angle makes it point upwards. Balancing the gravitational force with this vertical component of the surface tension gives us a formula to calculate the maximum possible mass of a water strider to be still supported by the surface tension of the water. Although the surface tension of the water is quite high, water striders still need to be light enough, otherwise they will submerge into the water just like the giant water strider in this cartoon.